This track is Stepping Stones, Adventures in Full Spectrum Embedded Exploitation and Defense.
Thank you. We know that we're standing between you and lunch, and we'll be very efficient with our time and put our New York voices on. We're from a small company called Red Balloon Security. We actually started life at Columbia University in an academic research setting, as I said, about 5 years ago, supported from DARPA, IARPA, DHS, to work on clean slate design of systems that would not be as insecure as we are living with and suffering with. Most everyone was focused on server security, web security, crypto, and we decided that what was being ignored was the embedded space. So all the embedded systems that are in servers, embedded systems that are sitting next to you in your office, and after considerable amount of effort, we developed a generic OS, device, product agnostic host security system called Symbiotes, software Symbiotes. And the primary function of this talk is to show you what is now achieved, having the world's first secure embedded systems sitting on this desk. But the first half will be offense. As I said, academic research is typically theoretically based, sometimes by observation. We proposed embedded system security. We had to demonstrate that embedded systems are insecure. And so you're going to see first half offense, second half defense. Let me introduce to you Ang Sui. He'll be presenting the work that we've done together. Michael Costello, Jatin Kataria, and I'm Sal Stolfo.
Okay, thank you. So the title of this talk is Stepping Stones, Adventures in Full Spectrum Embedded Exploitation and Defense. The defense part is very important to me, so we're going to try to spend as much time as we can on the defensive part of this presentation, and here's why. Oh, and also the slides are not on the DVD, but they are on our website, and it's 100 megs. Sorry about that. Unicorns cannot be compressed, apparently I've learned. They're magical creatures that cannot be shrunken smaller. So this is the typical talk that we give at places like Black Hat. We spend some time thinking about and talking about the next shiny thing, be it, you know, a car or a printer or a phone or whatever other doodad that we want to look at and compromise. And then we go and try to compromise the thing, and we spend a whole lot of time in fail shack. So we're frustrated. We want to put a lot of this work and the path that we've taken into these slides to build up to the point where we find that one vulnerability, that one exploit that actually works. So we're very excited about it. We spend a lot of time talking about the actual attack. And then comes the bad news, right? This is the impact. And the news is always bad, and it more or less sounds something like this. Oh, so this device is something that's in our lives, and it's being used everywhere. The fix is actually pretty difficult, and you know, there's really not a perfect fix out there right now. And even if we had it, it would be difficult to distribute it out into the world. So we're all kind of screwed. And then we feel bad for saying that. And we follow up with, but it's okay, you know, like we have a duct tape fix, right? That will hopefully make sure your house doesn't fall down tomorrow. And that generally involves disabling a feature or pulling the device from the network or putting glue through the console port of the phone so nobody can actually get to it. And, you know, me being me, I always reserve some time for pictures of hilarious cats and things I find on Google image search, which amounts to harmless copyright infringement. And at the very end of this presentation, we always save a few minutes, a few slides to say, gee, this is a really big problem and we don't have a fundamental fix, so we really need a real solution. The solution needs to exist. Okay, bye, have a good day. And then we start this talk over again, right? So we've worked really hard today to make sure that this talk isn't that. This talk is a different talk, and we're going to spend half the time on offense. So we're going to show you new polyspecies malware propagation techniques that we've worked on, meaning malware that spreads from one type of device like a printer to another one like a phone to a router and vice versa in full mesh configuration. We're going to show you some very interesting 0 days we found in voice over IP phones. But we're going to take the rest of the presentation and really talk about the defensive technology that we put forth. This is work that I've done at Columbia University. This is essentially the output of my PhD career over the last 5 years. We've thought very hard about this problem, the problem of legacy embedded devices and their security problems. And we came up with this thing called Software Symbiote that is now being transferred into a company called Red Balloon. I don't want to spend some time explaining this technology to you and showing a lab with this technology live on stage. And of course, I'm going to save some time for pictures of unicorns and other things I find on Google image search at 4 in the morning. So the human cast of characters, we already went through a little bit. Dr. Sal Stofo is a professor at Columbia University and also co-founder of Red Balloon. Michael Costello is a scientist at Red Balloon and also fashionista by day. And Jatin Kataria is a scientist at Red Balloon. And here's me. My name is Ang Tsui. I am a local man. We have very special guest appearance by Mikey Drop Tables, right? Who is the mayor of Pwntown, which is located halfway between Quarth and New Jersey. Okay, that's where it is. And that's not all. I'd like to reintroduce to you the modern office, right? So here is the cast of machines that we brought to you on stage. The first one is the Cisco 2821 router. You may not have one on your desk, but you probably have one somewhere in a closet somewhere. And this is more or less responsible for the routing of your office. Next, we have one of my favorite pieces of hardware, the HP LaserJet printer, the 2055. And then we also have the Cisco 7961 IP phone, which I'm sure you guys have all seen in the last decade. And here's the bright, new, shiny, sexy brother of this phone, the Cisco 89000 and 99000 series phone. And this is the one we're going to show a zero-day attack on. But this has already been reported to the vendor, and I believe a bug fix is out and a patch is out, so please go and update your phone again. Now, we also threw in an 1841 router, and we're going to spend a little bit of time talking about our work on the Avaya phone. So here is a layout that we're all very familiar with, right? On top, you have the big bad internet, and on the bottom, you have your intranet. And apparently, Pwntown is located on the right side of internet, where Mikey Drop Table is mayor. So to people of Pwntown, your internal network is a mystery, right? They don't really know what's going on inside. They can't scan into your network because this firewall prevents all the traffic from outside from getting in. But Mikey Drop Tables can make educated guesses about what's probably inside your network. And he says, well, there's probably a printer in there somewhere, right, that people use to print documents. So what Mikey Drop Table does is he makes a really fantastically great resume, right? And this resume will impress some people inside the organization so much that they would want to be compelled to print it out on the printer. And as we've talked about a year and a half ago, there were vulnerabilities inside a large number of printers that allowed a print job to actually modify the firmware of the printer itself, right? And from there, Mikey Drop Tables gets a physical entry point into your intranet, and then you can start thinking about all the interesting things you can do with that. So I want to say that the printer that we're showing has the vulnerability that we talked about 18 months ago. This is a vulnerability that the vendor has patched already. And why am I talking about it still? Well, it turns out we collected quantitative evidence by scanning IPv4, looking for these printers on the internet, and we found that 14 months after the firmware update has been released, the global patch rate, as far as we can observe, is 7.4%, right? So this tells me, A, most people don't update their printers despite very serious security vulnerabilities being announced, and the fact that the updates do exist. And two, the 7.4% patch rate really is attributed to new printers being brought online, right, as they're being bought by consumers over the period that we measure. And this is a problem. So I'm talking about this vulnerability still because unlike, let's say, a vulnerability in Firefox or Chrome, where you have a lifetime of maybe a week, right, if you're lucky, a vulnerability that I find on an embedded device like a printer or a router or a phone will most likely live for years without being fixed, right, because we don't have the patching infrastructure that we have on the desktop on these embedded devices. And also, people are generally afraid to update the firmware of these mysterious devices that we don't want them to break. So here's what happens. Mikey Drop Tables owns a printer, right? And what he does then he creates a reverse IP tunnel out of the corporate firewall, right? Punches a hole through that back to the internet, where he can then use this tunnel to send command and control packets down to the device as if he was physically located on your local segment. And from there, if everything works out right, you can use that command and control and other modules on the printer to start doing standard reconnaissance of the network to figure out other embedded devices, other phones, other printers, other routers inside your environment. And if you're super good, you can then drop exploits and implants on all of these devices, and the process repeats and repeats and repeats. So I did some of this work, and it turns out if you look at every individual device that we've looked at, the process really wasn't, I mean, it wasn't easy, so I have to put easy in air quotes, but if you had the device, you had the physical device, you can take it apart, you can look at the code, you can JTAG into it. Finding vulnerabilities in these things weren't really all that difficult. So we did it for the printer, did it for routers, and we did it for a number of different phones. So I added this page actually as the first page of my candidacy document at Columbia about a year ago, where I was pretty convinced that polyspecies malware propagation, if it doesn't exist already, is going to be something that exists fairly quickly. Because I did some back of the envelope calculation estimate of how difficult it would be to really bring all these things together. And it didn't seem all that difficult to me. But then I started doing it and I realized that there are certainly some challenges you need to solve. So polyspecies malware propagation on embedded devices, much more difficult than on, say, a group of Linux machines. And so what I really want to do is, let's say I want to get initial entry through an embedded device, and from that have full mesh propagation to other embedded devices that run on different operating systems. Some are open source, some are very proprietary, on different hardware architectures being MIPS, ARM, x86, AVR, who knows what, PowerPC, and have it propagate itself through the network and have it operate semantically as a cohesive unit that supports the same command and control on every single device. Now, this is why it's difficult. So if you look at the cast of characters, we have devices from 3 different vendors, right? Well, yeah, 3 different vendors. And we also have operating systems or hardware architecture that's MIPS and ARM, very different flavors of it. And some of them we've seen PowerPC, x86, AVR. So the diversity is really the thing that gets you. And on top of that, they run operating systems that we may or may not understand. So, if something runs a modified version of the Linux kernel, I have some understanding of how that works, right? But if something's running a very proprietary thing like iOS, where I'm not allowed to get any access to source code or proprietary information, I would have to reverse engineer all of that, and that's quite a cumbersome process. And then there's CNU, which is somewhere in between, Cisco native Unix, kind of like Unix, but not really. So this is why writing the same rootkit, let's say, for all of these devices is pretty difficult. Now, I'm going to take a step back and say we identify the challenges that need to be solved in order to get polyspecies malware propagation to work on these devices. And when we solve the offensive problem, we're actually solving the dual of the defensive problem. So the techniques that I'm going to show you on the offensive demo is exactly the same techniques that I will show you on the defensive demo, right, to make both of these things happen. And at the end of the day, our goal is to get arbitrary, generalized, reliable execution on whatever endpoint there is, regardless of the hardware platform and regardless of the software operating system running on these devices. So, very first challenge that we have to solve is obviously binary modification. How do I even get my binary onto the device at all? Be it through a live attack, memory modification attack, or by crafting a firmware update and putting that onto the device through the regular firmware update process. That actually has been solved. So we created a system called FRAC, which we talked about briefly at Black Hat last year, that has basically solved this problem for us. So if you're interested, please check out the slides from Black Hat 2012. Now, the next question is a little bit trickier, right? How do I do generalized execution? And by execution, I really mean, how do I run the same code, the same semantically equivalent code on environments that have different processors, different operating systems, right? Different environments that may or may not be proprietary. Now, if you solve that problem, you still have one more problem to solve, and that's even a little bit trickier still. And that's getting generalized input and output to these endpoints. And this is typically hard, right? Because in order to send a packet, you're going to have to understand, for example, the socket library interface, right? At least, the driver that talks to the Ethernet PHY to be able to actually send a raw frame, and that's very device specific. But it turns out we found a way around that, at least for the input part, and it involves using the solution from the generalized execution problem that we talked about previously. So let's talk about generalized execution. So forget everything you know about every operating system. Just imagine you have a black box on the network that computes. We can make an assumption that this box has some piece of memory, and in that memory there is a region of code and there's a region of data, and a part of that data memory region will dedicate to something we call generally the I/O memory region. So in this code section, right, there's going to be pieces of code that are there that are probably not necessary for the operation of the device because firmware is bloated, and this doesn't really surprise anyone. So I'm talking about things like the debug messages, the syslog code, IGMP code, things that aren't configured and it will never be used, but is still present in the firmware of the embedded device. On the other hand, we actually know that there are many points inside the code that will be guaranteed to be hit periodically at a high rate, regardless of the operating system. And this is by looking at the ISA about how MIPS and ARM works. And a very good example of it is the ERED instruction. We know that on this device, regardless of the operating system, exceptions will periodically happen. And when they do, the ERED instruction will be called. So once we hook the ERED instruction, we get perpetual execution on that device, regardless of the operating system that we're working inside. Now, let's put these two things together. We take a piece of unused code region and we replace it with our own payload. Now, this payload could be an offensive payload or a defensive payload. It really doesn't matter. And we're going to take some other pieces of memory from the code section and use it for our stack area, for our heap area, our general dynamic memory use area. And when we have that, we're going to make a whole lot of different hooks. We're going to hook all sorts of places in the code where the CPU will eventually hit, so that we guarantee that we have perpetual periodic execution of our payload as the host program is running. And that more or less is the generalized execution solution. It may take you some time to convince yourself that this does actually work reliably, but we're going to show you live on stage, both in the defense and offensive demo, that it does work, and it does work pretty well. So let's take this and solve the generalized input and output problem, right? So instead of a rootkit, let's make a packet scrubber. This packet scrubber will run periodically as the host program is running. Now, all this packet scrubber is going to do is it's going to identify the I/O memory range and do a linear scan of that memory range, looking for specific predefined patterns. Of course, we have to hook it to the intercept points first. And the patterns are something that we define. So we're going to call these CNC command patterns that correspond to commands that we would like this device to do. And as the device is talking to things on the network, various packets are being received and copied into general purpose memory range, and that pattern will eventually end up in the memory range of the device, right? So I'm not talking about just well-formed packets either. We can ping the device with a payload that contains an ICMP or a CNC control pattern. Or we can send, let's say, an email, right? If the device is a store and forward, the content of that email will contain the content of our CNC pattern inside a JPEG, for example, right? So we can send, as long as we can get this pattern onto the memory of the device, our packet scrubber will eventually identify it and process it. So as the device is running, these commands are coming in and the packet scrubbers are identifying it, and it's punting it up to this little processor that figures out, is this a valid packet? And if so, what does this packet allow me to do? Does it contain code that I want to execute? Does it contain memory exfiltration commands or memory modification commands? And that's how we do generalized input. Now take a step back and think, have I devised the thing that's specific to ARM, right? No, this will work on MIPS, it will work on AVR, x86, PowerPC, whatever it is that you want to throw at it. And does this only work on VxWorks? Nope, right? This will work on Lynx OS, it will work on the CE kernel, it will work on little iOS, big iOS, Linux, whatever it is. Okay, and for completeness, this is the structure of the CNC command and acknowledgement that we defined for this demo. If you notice, here is the envelope. The envelope contains on top a predefined pattern, OXACACAC, it's my initials, right? Some metadata about the transaction. And at the end, we have an ending pattern, and right before that, we have a checksum value. So this allows us to identify the CNC command packet in memory and then validate the integrity of it before processing it, because we are doing a linear scan where we don't really understand how the I/O subsystem works. So it is a possibility that our CNC commands will be corrupted as the system goes. We'll have to, so this is the way for us to validate. Okay, and then once we validate the envelope, we start processing the payloads and arguments and the commands inside each one of these things. So put it all together, right? You have your generalized execution, you have IOMEM scrubber, and as the device is doing its thing, various CNC commands are being copied into IOMEM, they're being identified, they're being processed, right? And once it's processed, the device does the thing and then possibly exfiltrates some response back out the network. And that's how we did our offensive demo. Now, we heard about Barnaby Jack probably the same time everyone else did here, and we knew that we had to do something special for him as a tribute in our presentation. So for the last few days, we've been working pretty hard to put this function together. And this is the Barnaby function. What it does is it takes as input arbitrary embedded devices, right? As output, it produces a device that has its face inside the binary of that device. Okay, so we're going to show you that live on stage. And then we also made a modified Barnaby function that does exactly the same thing, but writes permanently to the storage. Now, I don't know if you guys heard Monk's talk about MTD devices and NAND flash, but we did this without knowing about your talk, and we could have done this in a much more elegant way had we did this, yesterday. But if you haven't checked it out, definitely check out what Monk did. Super cool. But we found another way. It's less elegant, but it still works. It puts Barnaby's face into flash and permanently destroys the device. And that actually is our sacrifice to the demo gods, because we do respect the gods, and this is a very complicated demo with no backup video. So here it is. In Barnaby's honor, we've destroyed a Cisco phone. His face is inside the boot flash. So now we're going to talk a little bit about the demo. First, so here's your local segment. Let's say it has a printer, and there's Mikey drop tables. And what he's going to do is compromise the printer, have a reverse tunnel back through the firewall so he can send command and control packets. The first thing he's going to do is have this printer recon the rest of the network and find out things that are listening on various ports that we're interested in. After that, we're going to start doing more network reconnaissance, pick up the MAC addresses, figure out the vendors, and poke at it to figure out whether we're looking at routers or phones or printers or whatever it is. And then we're going to show you various ways of using the printer as a stepping pone. That's the name of the talk, right? And to compromise other devices on your network and show you possibility of full mesh propagation. So getting from the printer to the phone and using the phone to propagate to another printer, vice versa. Okay. Oh, right before I do that, I really have to give a big shout out to Joe Gran and the JTagulator. The work that we did on the ViaPhone was made super simple and super fun because of the JTagulator board that he built. So if you see Joe, buy him not beer, but a whole bunch of cider, and then buy 10 of these boards. This is a fantastic piece of hardware that everybody should have. So big ups to Joe. So now Mike is going to start the console, and he lives in Pwnetown. Okay, so we're no longer in your internal network. This cable represents the internet, right, where we're connected to some piece of equipment that connects to the corporate network.
Okay, so we have our server started, and at this point, the printer has made a reverse tunnel connection through the firewall out onto the network and is now connected to our machine. So, and just so you know what you're looking at on stage, everything on Sal's side is Pwnetown. This is the offensive part of the network. Everything on the left side is the defensive part of the network that we're going to show later on. So since we're doing offense right now, let's turn on our offense console. And our offense client. Okay, and we already have the printer added to the network. So, so this is the printer that's sitting in the network. My console is here in Pwnetown, and we're going to start doing nasty things within the network from outside the firewall. So the first thing that we're going to want to do is we have one foothold in the network, but we want to start using this foothold to see what else is in there. As Zong said, we want to do some reconnaissance. And so what we're going to do is a SYN scan directed to the printer, and we're going to scan on TCP port 23. So I'll say this at the beginning, but then please remember that this is what's happening throughout the presentation, that I'm sending this command through a command and control tunnel to the printer to instruct the printer on what to do. I also want to make the point that the stuff that we're showing right now is not any new exploit of the HP printer, that this is the same work that was shown about 2 years ago at 28C3. There was an academic paper this year at NDSS. We're using, HP had released a patch for that exploit. The software that's running on the printer that we're exploiting now is software that was, that existed before the patch was there. So we're running somewhat old software on this, and we're not doing any new exploit work. We're just making the printer do new and more interesting things this time. So we SYN scan the printer, and now we start seeing that we're spoofing the IP address of our Pwnetown station, and these SYN ACKs and resets are coming back, and so we can start to see what other devices are on the network, and these are our recon targets. One of the other things that you can also see here is that the printer is now identified as an HP LaserJet P2055DN running firmware from 2010, March specifically, and that it has a fingerprint with 8 hexadecimal digits. And so what this fingerprint is a memory fingerprint that is that's calculated by the rootkit that's running on this printer, and it's exfiltrated in the command and control acknowledgement packets. And then what we can do with this is use this key as a lookup into a dictionary to find out information about the printer, such as the name. That's all pre-computed before we start looking at this. So the next thing that we want to do is we have an idea of some devices that are in the network, but we want to start finding out some, we've got some layer 2 information, but now some layer 3 information, but now we want to get some layer 2 information as well, because that's going to help us with the next stage of our attack. So we have a command in here called down low, which again over the tunnel is asking the printer to return a MAC address mapping to the IPs that we have. And by looking at the first 6 bytes of the MAC address, the vendor OUI, we can find out an idea of what is running on the network. And we can see now that we have a number of targets that are from Cisco and our HP printer. And the one that we care about and that we want to demonstrate on here is target Recon 4. And because we set up this network, we know that it's a phone. So we're going to rename Recon 4 to phone 2. And so now we're going to go after phone 2. And the way that we're going to go after that is we're going to attempt to SSH into it. We know that the phone is configured for SSH, but we're going to assume that we don't know the SSH password. What we're going to take advantage of is a design feature of these phones that whenever you attempt to SSH into them, their response is that they're going to ask their pre-configured TFTP server for a copy of the authorized keys file in which to do key-based SSH authentication. What we're going to do is instruct the printer to ARP poison the phone, making it think that the printer is the TFTP server on the network. The printer is also going to additionally not only be scrubbing for command and control packets, but it's also going to be looking for a specific pattern of an authorized keys file TFTP request. When it gets that request, it has already loaded into memory that fits in one TFTP response packet, an authorized keys file that is going to populate the proper source, destination, IP, and UDP port information and send it along to the phone. So what we're going to do right now is set up our command to poison phone 2 with the IP address of the TFTP server. We're going to start our proxy here, and we see that the printer has connected to it. Excellent. We're going to queue up our SSH command. We're going to send it some ARP poisoning, and maybe a little bit more for good measure. And now we're going to SSH in. So what we're doing is we're SSHing now from my local host through this proxy connection that the printer has built to my machine, through the printer to the phone, ARP poisoned, grabbing the TFTP request file with a response file, and now we're presented with a shell login instead of an SSH password prompt.
Wait, but Mike, how do you know the username and password for this phone?
Okay, well, this is actually pretty fortunate because pretty much all Cisco IP phones have default usernames and passwords. It's always default for user, and then the password is either going to be Cisco if it's a newer model, and user if it's an older model.
But you can change that, right?
No, you can't, because actually if you do change it, then it changes the checksum on the file system, and then the phone has to reset itself.
Oh.
So you can't change it.
That sucks.
Yeah. Okay, so we're sitting on this phone, and it appears to be running a Linux distribution from a company called Monte Vista. This is a Cisco 8961 running not the latest, but some fairly recent code 921. And this is the phone that's sitting right in front of Sal, way at the end, the shiny new Cisco 8961. And it's running a Linux kernel 2618. And so what we first started doing to look at how to break this phone, we decided that we were going to start looking for Linux kernel exploits either on x86 or an ARM that we could port there. And we wound up having a lot of difficulty with that. And so we decided that we had to look elsewhere. And in looking at, so we were going to try to do some file system tricks or some other type of trick. And we're going to, as Ong said at the beginning, we're not going to go through how we failed and how we eventually won. But what we did was we finally found out that these things are booted from NAND flash. And again, we wish that we saw Monk's talk because this probably would have made things a little bit easier. We noticed that it mounts at least one of its file system it mounts at least one of its file systems off of an MTD. And we noticed something kind of interesting about that MTD. And I have to type slowly because everything's going through this reverse tunnel.
Right, so this is live from Pwntown through the firewall, through the printer, SSH into a phone. And before he does that, I just want to say we spent a few days looking at vulnerabilities inside the kernel, and then we realized that this was a silly thing to do, right? So many people have already looked at the 2.6 kernel. We're probably not going to just be able to walk in and find another 0 day. So instead, we decided to look at everything about the phone that wasn't the responsibility of the open source community, right? The responsibility of the vendor, which eventually led us to this dev directory.
Okay, and so this is one of the devices, MTD4. So a question for the audience: does anybody notice anything that probably shouldn't be here? Just
and
shout it out.
Monk can't answer because he gave a really good talk about this. Yeah.
Yes.
Right. So the fundamental MTD block device that supports the entire file system of the phone is world writable. But that we can't do anything with it, right? Because we don't have the tools to write MTD blocks, or else we would have to compile it on the phone, and we have to bring in a compiler, and that's really hard, right?
Well, actually, you're wrong. There very fortunately are a number of Flash utilities like Flash Erase and Flash Info already on the phone.
No way.
For us
So
to use,
they ship the phone with the tools, plus gives me permission to write the file system. That's nice.
And not only Flash, but we also have NAND dump and NAND write. So this is going to make our jobs pretty easy
that's
to be
super
able
cool.
to dump something.
But this is not going to work still, right? Because I can't ship like a 5 meg file system down to this phone. Even through TFTP, that's going to take forever. People are definitely going to notice. Right? I mean, this is complicated.
Well, there is in fact TFTP on the phone that will allow you to transfer it, so you don't have to do any weird console escape tricks. But you don't need this enormous file to transfer onto this thing. What you could do is you can pack up a tiny little file system that contains exactly one file and drop it into a 4K block, transfer that over to the phone, and then use these utilities to dump it. And then when the phone boots up, it'll mount it.
Wow, and what binary would you want to pack into that one file system?
Well, what I would want to pack into that is maybe something like this file here called rootkit that is owned by root and has a sticky bit set. So if I look at who I am,
You're nobody right now, but that's going to change.
I am default, but if I run our rootkit file, I have root now.
Ta-da! So that's what it took. And when we saw this vulnerability, I was a little disappointed, right? Because we're moving away from the CNU kernel, from proprietary code that's written 10 years ago without proper testing, to the Linux kernel that has been backported with all of the security vulnerabilities that we've known about for the last 4 years. And it turns out it's now easier to compromise this phone than its predecessor. So just because you have a secure kernel doesn't mean that the vendor, the way you package these things, will not allow a single mistake to have the attacker completely own your phone. Of course, when we have root on this phone, we can do everything that we've done on the 7961, exfiltrate voice information. And another thing that is super nice is that we're now on a Linux machine, so we're home free. We can start building all sorts of stuff on this guy and then start using that as a propagation point to, let's say, I don't know, own another printer, right? And this is how the full mesh propagation will work. So now we've shown you this ODE. Let's show the offensive network with our malicious implant that we talked about working on a number of devices. So for good measure, we added 2 other devices, a Cisco 2821 router and a Cisco 1841 router to the phone and the printer, just to prove to you folks that this command and control infrastructure will work on ARM and MIPS, on different architectures, on Linux and on operating systems that we really don't understand.
Okay, so we have our console reloaded. Now we have all of the devices that are already running our packet scrubbing rootkit on them, the printer, the phone, and the 2 routers. So we have our packet scrubber in there. Let's start running this thing through the paces. So what would the well-equipped hacker want to do? Maybe he or she would first want to heartbeat these printers, or heartbeat these printers, phones, routers, and whatnot, and see what they are. So let's send a heartbeat to all of the devices through the command and control tunnel to the printer. And we get some information back. Again, all of the command and control acknowledgement packets have these memory fingerprints in them, and then which we can use these as keys into a pre-computed database to find out information about the firmware that's running on them. So we could, for instance, type in get info on the phone, which is a 7940 or 7961, and we see that that's the firmware. We know that it's a MIPS 32 big endian processor. We can identify through again pre-analysis the location of a number of either third-party libraries or a number of functions, but we decided not to include any information here
because we got Attorney Pwn, and they said that this was a really bad idea to reveal, and it is. So. A little side note, the memory fingerprint idea was something that we came up with for the Cisco iOS router rootkit that we did a few years ago. That idea was basically we find features of the code, like the ERED instruction, and we run a very quick hash around that, the addresses of all those, and that yields a unique fingerprint that identifies the specific hardware and software version of that particular embedded device and the software running on it. And it turns out this is not specific to iOS or routers at all. This is something that will work on printers and phones and cars and Predator drones, I'm sure. So we've done it on all of these devices too.
Okay, so the next thing that we might want to do is to read memory. So let's see if we could read memory on the phone. And we're going to try to read from 800F1650. So we're sending, again, a command and control packet over the server, over the reverse tunnel to the printer, to the phone, asking it to read. Let's try that again. Okay, so this is, we're just reading a bunch of zeros from memory, so we can probably write to it at this point and not make any really nasty changes to it. So let's give that a try.
Now, as Mike is doing that, he's sending an ICMP packet through the tunnel, right, from Pwntown through the router to the printer, and the printer then proxies that command and control as a UDP packet going into the phone, right? The phone is then going to run the packet scrubber, finds the payload, and then generate a command and control acknowledgement in the form of an ICMP request with the body of the payload containing the memory that's being exfiltrated. So the point is, the actual network header of these command and control packets is irrelevant. It doesn't matter if we put the response in one thing and the acknowledgement in another. The only thing that matters is the content of the payload.
Okay, so here we can see that at the previous location, we actually wrote OMG it works into it. So now let's show everybody here may or may not know typical Cisco router behavior. This is the 2821. If you type in enable to get into super user mode, if you type in the wrong password, it says bad secrets and you're just still at the regular user prompt. And also if you type in show version, it gives you information about the router.
So let's rock the Barnaby function.
So let's rock the Barnaby function. So we could Barnaby the router 2821. And while we're at it, let's do the 1841 as well. And so now if we type in enable and we get bad secrets, we still are at privilege level 15 super user on there.
Oh wow, that's not supposed to happen.
No, it's not. So it patched the function that returns the value of it. And if we look in show version, we see our friend who will be missed.
Ta-da! You do have to tilt your head a little bit, then you'll recognize them.
Yeah, and we got it on the 1840.
So now we have universal read, write, execute capabilities on every single one of these devices, and we can pre-compute the memory layout of every single one of these things so we can make precise modifications to these devices without guessing where a particular function is. And we can do all of that pre-computation offline, stored in a big database, and we can do this to any embedded device that we encounter.
Okay, so that's it for the offensive demo.
Great, awesome. So let's switch back to the slides. Okay, and just one thing I want to talk about, and this is something really, oh, by the way, so with command and control offensive payload implanted into all these devices, the Pwntown population has now increased to 6 because Mikey is one of them, right? So here it is. This happened to your network because a resume, a malicious document, was printed onto an unpatched printer. And I don't think that's a far-fetched attack scenario. People do this all the time. But when that happened, the rest of your network, all the embedded devices where you still have 0 visibility on, has all been compromised, right? And this is something that will remain in your network for a very long time and will most likely go undetected. So this is bad. Some fun facts that we found out about. It turns out the 2055 printer is a shockingly capable printer as far as a networking piece of equipment goes. We were able to get it to send about 15,000 packets per second with almost no code modification. Just put it in a loop and it just yaks all day, right? Great. And if you take this and try to denial of service a Cisco router, for example, we had a 2821. It turns out a single 2055 printer wins all day. I can peg the CPU utilization of a Cisco router to 99% by sending malformed TCP packets to the OSPF hello address, right? It should never receive it, but once it does, it just blows up. So that happened. That totally works. If we have time, we'll show you. Now, as promised, we're going to spend the rest of this presentation talking about the defensive work that we've done. And it's important to point out the software symbiote solution is designed to be practical and designed to be something that can be retrofitted into all of these vulnerable embedded devices that exist today. I care about securing things that exist today, not so much reinventing the wheel. And in the future, we're going to build PS7, right, on every phone and printer and whatnot. With that said, the technology requires 0 hardware modification, 0 specialized hardware, and it does not require any proprietary intellectual property from the vendor. We require no source code. We operate purely at the binary level. The source code that you get from downloading it from the vendor's website is the thing that we take as input, and the output we generate is a modified symbiote injected firmware that is functionally equivalent, that has host-based defense capabilities. So I'm going to turn it over to Sal. Oh. Okay. So here it is. This is basically what I've been doing with my PhD for the last years and years. About to see it in a little console. And on it, we have the software symbiote injected into all of the devices you saw in Pwntown. We have the HP printer. We have 2 Cisco routers, and we have a Cisco IP phone running on MIPS and ARM, VxWorks, all sorts of different operating systems, but all working exactly the same way, continuously sending dynamic firmware integrity attestation signals to each other and also our alerting station. So this is different from timing-based attestation and static attestation methods that we've seen for a decade now, right? We've looked at the way those work, and there's some things that are lacking in that approach that the software symbiote definitely addresses. So let's start the console.
Okay. First, let's prep our phone. Okay, so we have, now we're operating on these devices here. We have the same phone as, we have a 7961G, we have a 2821 router, we have an 1841 router, and we have the 2055 DN printer. These things are, we have them all loaded into our console. We're now on the, we're no longer in Pwntown. This is, we're inside the network. We're monitoring the symbiotes. All these devices are already running software symbiotes that we put in there without any vendor source. All work that has been supported by DHS, by IARPA, and by DARPA, all packed together with FRAC, which was generously supported by Cyber Fast Track. So thank you, Mud.
And Mudge, thank you.
So what we're going to do here is we're going to start going through these devices one by one, running exploits that we've demonstrated before, and the symbiote is going to detect them and alert them. You're going to see a checksum for all of these. That the symbiote is constantly sending a heartbeat with a checksum reporting that it is okay. If it detects a firmware, a static region of memory change, that checksum will change. It'll report it to this monitoring station, and then we'll be able to go from a secure state of secure to a state of pwned. The first thing that we're going to look at is the 7961. So we're already SSH into this. This is a 7961. This is not a new exploit. If you want details on that exploit, please see our 29C3 presentation, Hacking Cisco Phones. And what we have on here is a preloaded binary called pwnbin, that if we run it, it makes a change to the setuid program so that if we attempt to log in, oops. We have root access, but that required a memory change. So now if you look in the upper left-hand corner, it's changed from secure to pwned. So now we can start rolling through the other devices. First, the 1821, or the 2821 rather. So we're not going to be demonstrating a Cisco iOS exploit here. In addition to loading in the symbiote that's monitoring the secure state of this phone, we've also modified the show CDP neighbors function. And what the show CDP neighbors function does, besides showing our CDP neighbors, is it makes a small change to memory, the change that the Barnaby function made to allow us to do enable authentication bypass. So if we do a show CDP neighbor, it's changed the state of the memory, and now the 2821 has also now gone to pwned. We can do precisely the same thing on the 1841. And finally, the printer is also running a small symbiote in it. And the way that we're going to demonstrate a memory modification there is using the command and control to write to the printer at address 8010. And once we write to memory, that will change. The symbiote will detect it, and it'll be reported as it's been pwned.
Ta-da! So I just want to point out that you folks are literally the first public audience that has ever seen any type of device like these. So we've had printers and phones and routers for a long time, but these are the devices, these are the only devices in the world that has host-based defense built right into it. There is no other printer on the planet that can tell you whether the printer has been compromised through an exploit, except for literally that one sitting over there on this table. Right? And we're trying to change that so that in the future, these devices will ship with host-based defense so that Mikey drop tables will just live in Pwntown by himself, hopefully. Now, so this is what happened, right? With the symbiote technology embedded into these devices, everybody stays not pwned, and Mikey drop tables is a super sad unicorn, which is exactly what you get in a Google image search when you type in super sad unicorn. It's like image number 3.
What you've just seen. Oh, is this working? Is this hot? Yes. What you've just seen is the beginnings of embedded system worms. It's not theoretical anymore. It's quite real. And embedded systems are ubiquitous. They're everywhere. They're in your doctor's examination room. They're in SCIFs. They're in your hotel room. Don't forget, what happens in Vegas may not stay in Vegas. This is a ubiquitous problem that has another set of problems associated with it. The legacy systems, to upgrade them so that they have host AV, there's no infrastructure to reach them. So this is going to persist for quite some time. New devices that roll off the manufacturing floor, they can have host-based defenses. But the vendors don't seem to be very interested in this problem, and that's because the market doesn't seem to care. We haven't seen large-scale exploitation of embedded systems, but it's inevitable. We need more of this, because it has occurred that embedded systems have been used for a number of nefarious activities. Are you aware of this exposure of the security system, the locking system of Bentleys, for example? Volkswagen's response to it was to squash the research so it doesn't get presented at Usenix Security. It's an attack against the embedded system inside a car to protect them. And this, some of you may not be aware of it, but this gentleman was the darling of Wall Street. He was a hedge fund manager, made many, many millions of dollars. Every bet he placed, he won. And he was investigated, and sure enough, he used the IP phones in various financial institutions, bugged them to listen into conversations, traded against that as insider trader. He was caught. If he was caught, he succeeded, it doesn't mean there's nobody else out there who's doing it. Eventually, others will be caught. The most important thing at this point is when somebody looks at an embedded system, a phone, a printer, the particular devices that we have been playing with, it's not unique to HP, it's not unique to Cisco. It's the same problem. It's pervasive for all of the vendors and all of the different products. And that marketplace still doesn't look at security as a first principle property. It's function, form, appearance, price. But security now has to be considered as an important property of these devices. Otherwise, the market will scream for it as these kinds of devices are being used for exploitation. Finally, there's the government. Lenovo's now are no longer allowed to be purchased by US government because of onboard embedded systems that were discovered that do things that are not permitted, that are insecure. Government is also considering now this space of embedded systems and may require, as part of the GSA rules, that host-based defenses be provided for embedded systems in order for the device to be listed on GSA and then therefore purchased. And manufacturers are not going to make one product for the government alone and then one product for the commercial space. It's likely that the government will be the forcing function so that these devices then in the commercial space will be secured. That's our presentation. Software symbiotes are here and ready, and hopefully we'll have a bit more traction with the vendors that they will actually be able to ship with symbiotes next year. And finally, the end of our presentation, guys. It worked. You guys have no idea how hard we worked to make this work. Go over here. And lunch is in 8 minutes, but we're happy to take questions if you have any.
Actually, I just have one more thing. This is on. Okay, I have one more thing to say, and I hope we've worked really hard on this offensive demonstration for a reason. I wanted to convince the security community to show you folks that we've actually hopefully matured in our understanding of embedded exploitation. So we've always thought about things as, we own this one type of device and then we can change the functionality of that device. Own a printer, you can steal a print job, right? Own a car, maybe you can get it to stop and whatever. And own a phone, you can listen to what the phone is actually saying. But we're now entering a different age where any one of these embedded devices that are vulnerable, that it lives on your network, has absolutely the potential to completely compromise the security posture of your entire network, and it can do it in a way where you absolutely have no visibility, right? So this is something that requires a lot of attention. And when we think about defending things like the printer, right, we should no longer be thinking about defending the printer so it prints properly. We should be thinking about we need to defend this printer so that that printer can't take down our entire network. Right? I think this is where we need to start focusing. But before you tear down, can we see the printer kill a router? Do we still have that up?
I think we should probably wrap it up.
Yeah, let's take some questions.
Oh, I guess maybe not. Questions?
No, that's
Yes, sir? That's a very good question. So the offense.
Repeat the question.
Oh, right. So why could we why couldn't the adversary use the same hooking techniques to disable the symbiote?
Right. All they have to do is have seen the symbiote once and seen the computed checksum.
See, that's exactly, we've written 3 academic papers to address exactly that. The thing that I didn't really talk about is the offensive side and the defensive side comes from the same insight that you can get reliable code execution in these 2 different devices. The main difference between the offensive and defensive is that the defensive side, well, the offensive code doesn't actually care about getting caught. It cares about reliable operation. Whereas the defensive side absolutely cares about being caught, and it has to do this in a constrained environment without requiring specialized hardware, and we do that by using the principle of diversity. So every single symbiote injected device is actually a binarily mutated firmware that is functionally equivalent, that is completely randomized. So instead of choosing 15 different hooks on ERETs, right, for the offensive side, which is absolutely enough to run the packet scrubber, we go in and hook something like 15 to 45,000 intercept points inside the code of the host program, and we randomly choose those intercept points at every instantiation. So imagine every time a printer boots up or a phone boots up, right? It'll be functionally equivalent, but the intercept points are very different, and we choose these points using statistical mimicry attack so that the attacker can't simply say, oh, this section has way too many hooks for the normal code, right? We actually make it statistically undetectable or very difficult to detect for the adversary. And if you looked at a single symbiote, if you dumped the firmware from that, right, you would be able to get the binary layout of that single instance. And to propagate that type of attack across a network of binarily diverse, functionally equivalent devices all running the symbiote would be vastly different. And on top of that, we didn't really talk about it, but the symbiotes actually alert to each other as well, to not to the central console, so that when you exploit and disable a symbiote on, let's say, a phone, there will be a printer and there will be a router monitoring the symbiote protocol, because we really don't care what these devices are. And in order to have a successful disabling of the symbiote, you now all of a sudden need to have 3 successful attacks on 3 different architectures and 3 different operating systems that can be launched simultaneously, right? And when that happens, our external alert will figure out that 3 devices have dropped off the network. So this becomes not impossible, but significantly more difficult, and that's what we're trying to go after.
Yeah, and just one other point, what we developed at Red Balloon is a system called FRAC that was mentioned earlier on that automates all this. So every time you run FRAC, push a button, you'll get a whole new fresh diversified firmware that's completely different from the previous version. And so for large scale deployment, it's just automated, completely automated. Any other
And
questions?
these firmware images don't need to and shouldn't be generated on the fly. So every time a or Cisco phone boots up, we shouldn't be running FRAC to make the image. We really should be making tens of thousands of these images, encrypting them in a queue, so that, and having maybe the vendor or the organization sign this, right? So that every single time a device boots up, we decrypt the next one, send it out, right? Load the next one into the encrypted queue. So essentially, we're offsetting all of the computational cost of securing embedded devices off the embedded device computational resource. We can do this in the cloud, generate the firmware, put it into these tiny little underpowered devices, and have the security benefit inside the device, but have the cost of computation somewhere in a big iron in the cloud.
And there's a few other tricks that hopefully we'll present next year on the stage, and using randomization principles. So, any other questions? Good, we did it. Lunch is 3 minutes away. Thank you very much.